Dear students, today's topic is interference at an air wedge. In the previous class, we discussed the method of deriving coherent sources by two methods. One is division of wavefront, another one is division of amplitude. Interference at an air wedge. In this process, the two coherent sources are derived by the method of division of division of amplitude. The amplitude of the incident wave is divided into equal parts by partial reflection and diffraction, and hence two coherent sources are derived to produce the interference pattern at an air wedge. Air wedge means here two glass plates are kept parallel to each other. OA, OB are the two glass plates which are placed one over the other. At one end, the two plates are in contact. At the other end, a small space is generated between the plates by keeping a very thin material like a paper piece or a thin blade or a very thin wire, using such objects or placing such objects, inserting them. At the other end, a small space is created so that a thin film of air is enclosed between the two plates, whose thickness at one end is 0. It gradually increases as we move towards the other end. Thickness of the air film gradually increases as we move from the point of contact to other end, where an object is inserted or a space is created. So this is the thickness of the air film. Actually, a very small thickness in micrometers is introduced between the plates, but here for convenience I have taken the thickness this much. Actually, such a large thickness is not there for the air film inside. A very small thickness in the order of micrometers. See, this is the setup. Here we have two glass plates kept one over the other. At one end they are in contact, at the other end a blade is introduced. Such a thin film of air is enclosed between the two glass plates. And when this system is illuminated by monochromatic light is made to fall normally on the setup, and see here, the light falls normally on the setup and light undergoes. See here, OA, this is the upper surface of the air film. From there, the incident light gets partially reflected and partially refracted. That refracted ray falls on the lower surface of the air film inside. From there, again it gets partially reflected and partial refraction. This reflected ray again falls on the upper surface of the film. There again it gets refracted to air. And these two rays, they travel in air, are the reflected rays from the air inside the two plates. And these two rays, they behave like the coherent rays to produce the interference pattern. And when this setup is viewed from the normal direction using a traveling microscope, the interference pattern consisting of alternate bright and dark bands is observed in the field of view. And there we observe the straight line fringes. The straight line fringes are observed. All the fringes are parallel to one another. They are straight line and parallel to one another. And all the fringes are equally spaced there. Light is falling like this. So the pattern consists of the fringes in this way, in this plane. All are straight line fringes parallel to one another, and all are equidistant, and all are having equal thickness. And at the apex means this point, the fringe is always dark. Then bright dark. In this way, alternate bright and dark fringes are observed in the field of view. This is how interference pattern is produced using coherent sources produced by division of amplitude in this interference at an air wedge. The fringes here, why the fringes are straight and parallel? Here say, the light is falling on the surface normally. There, the reflected light, it gets reflected from all the points having equal thickness, all the points of air having equal thickness. So locus of all those points is a straight line, all those points having equal thickness of air, so that the fringe will be a straight fringe and all the fringes are parallel to one another. The fringes are also called as a localized fringes. They are localized in this air film. Now the theory of is interference at the air wedge. Actually, the use of this method is to, one can determine the thickness of the material inserted, either blade or the paper piece or the wire inserted. The thickness or the diameter can be determined by this method if we know the wavelength of the incident light. When lambda is known, the thickness or the diameter d can be determined. The theory is, see here, OA, OB are the glass plates. D, the thickness or diameter of the material inserted at this end. If it is a wire, diameter; if it is a blade, it is the thickness, or paper piece, it is the thickness. Fringe pattern is observed in this air film there. Air film enclosed between these two plates. This shape is called the wedge shape. Now let us consider the mth dark bright fringe. Consider the mth bright fringe at one position. Say at this position, consider the mth bright fringe formed. Let PMQM be the thickness of the air film at that point. Now the next bright fringe, it is PM plus 1, QM plus 1, formed at this point, having thickness slightly more than the mth one. In this way, the thickness of the air film goes on increasing. Here we have the two fringes, mth and m plus 1th fringe, one after the other, two successive. First one fringe, the next where we get the dark, then the bright, two successive bright fringes. In between we have one dark fringe. Consider those two bright fringes. And here interference produced due to reflection of light. And we have derived already the condition, general condition for interference in reflected light. For bright fringes, the condition is 2nt cos r is equal to 2m plus 1 lambda by 2. This is the general condition to produce the mth bright fringe in reflected light. 2nt cos r equal to 2m plus 1 lambda by 2. M, order of the fringe, mth one, lambda, wavelength of the incident light, T, thickness of the air film or the thickness of the medium, here this is the air film, N, refract index, R, angle of refraction. See here, medium is air, for air N is 1, and the angle of refraction here is very small, so that cos R is approximated to 1. Since R is very small, cos R approximated to 1, so that this condition becomes 2t is equal to 2m plus 1 lambda by 2, where t is the thickness of the medium. And if we apply this condition to the mth bright fringe produced here at the position PMQM, thickness is PMQM, so that this expression becomes, say T is PMQM, the expression becomes 2 PMQM. What is this PMQM? Just the thickness. Symbolic representation of the thickness there equal to 2m plus 1 lambda by 2. This is the condition to produce mth dark bright fringe at this position, having thickness PMQM. Let the equation be 1. Now let us consider the next one, m plus 1. What would be the condition? So the same expression becomes 2 pm plus 1 qm plus 1. See, this is the thickness. So pm plus 1 qm plus 1 is equal to 2 into, in the place of m we have put m plus 1. It is a m plus 1th fringe. So in the place m put m plus 1, then one more plus 1 lambda by 2. If you simplify, you get 2m plus 3 lambda by 2. This is 2 pm plus 1 qm plus 1 is equal to this much. Equation set 2. And we got the expressions for the thickness in terms of the thickness of m than m plus 1. Now 2 minus 1. 2 minus 1. Subtract. Left hand side is 2 common. Pm plus 1 qm plus 1 minus pm qm is equal to right hand side. If you subtract this minus this, you get 2 lambda by 2, nothing but lambda by 2. Or it is, minus, subtract, you get lambda, or pm plus 1 qm plus 1 minus pm qm becomes lambda by 2. 2m plus 3 lambda by 2 minus this equal to 2 lambda by 2, that is lambda. So this becomes equal to lambda by 2. What this equation indicates? The two successive bright fringes. Two successive bright fringes, meaning the bright fringe, one bright fringe, the very next bright fringe. The distance between them equal to lambda by 2. The difference, the thickness difference. The thickness difference in the thickness of air film for two successive bright fringes is lambda by 2. Then, if we consider the m plus m dash the bright fringe, m dash 1. Means here from the in between the space qm plus m dash, there are m dash number of bright fringes. For this m dash bright fringe, this is the thickness. So then this particular fringe is always formed at a thickness equal to m dash into lambda by 2. For every bright fringe, formation of every bright fringe, the thickness increases by lambda by 2. So for m dash bright fringe, thickness of the air film will be m dash lambda by 2. I think you might have understood this. For m dash, that particular bright fringe, thickness of the air film increases by m dash lambda by 2, where lambda by 2 increasing thickness of air film for one bright fringe. So that what happens then? If the thickness increases by m dash lambda by 2, so that the difference between Pm plus m dash, Qm plus m dash and Pm Qm will be equal to m dash lambda by 2. The difference is the thickness corresponding to the m dash bright fringe given by this. Now here we have done the construction. From this, draw a perpendicular. It is PMC and let theta be angle of the wedge. The angle of inclination between the two plates. Angle of the wedge. So here, in this triangle, see, PMC, PM plus M dash, this small triangle. If in this triangle, if we define tan theta defined as opposite side by adjacent. Opposite is this, adjacent is this. So that we get this, opposite by adjacent. And the opposite side, it is PM plus M dash by C. This one is nothing but, see, this length is nothing but this full length minus this. Look at here, this length PM plus M dash C is equal to this full length minus this, and the C QM plus M plus M dash, nothing but PM QM. What is PM? See, PM QM, thickness of the air film at this point. So that your tan theta becomes this minus this divided by PMC. PMC, nothing but QM plus M dash. Let that separation be taken as x. Let this distance be x. So that our tan theta becomes m lambda. This separation already known. Already we have m dash lambda by 2. So m dash lambda by 2 by x. That is tan theta. If theta is small, when theta is very small, such a small angle is when they are kept on each other, very small angles made between the two plates, theta small, so that tan theta is always approximated to theta. Sin theta approximated to theta, cos theta approximated to 1, so that tan theta approximated to theta itself. So that this expression becomes, this one becomes theta equal to m dash lambda by 2x. Or from this, you can write x as x equal to, theta comes here, m dash lambda by 2 theta. This is the expression for x. What is that x? Distance between the m and m dash bright fringe given by m dash lambda by 2 theta. Or from this, if you take m dash this side, the expression becomes x by m dash. M dash this side comes in the denominator, x by m dash is nothing but the ratio of distance between m dash fringes. X is distance between m dash fringes, m dash number of fringes. So x by m dash nothing but width of one fringe, also called fringe width. Separation between any two bright fringes. It's given by x by m dash, nothing but fringe width beta given by lambda by 2 theta. Thus, here the expression for fringe width beta. What is fringe width? Distance between any two successive bright fringes or any two successive dark fringes. Here we have considered bright fringes. We got the expression as beta equal to lambda by 2 theta. If you consider the dark fringes, again you get the same expression, indicating that all bright fringes and all dark fringes are equally spaced. Fringe width remains constant for all the fringes. So beta is lambda by 2 theta. Now, this is how beta can be determined if lambda is known. Or if beta is measured, lambda can be determined. In that case, one should know the value of theta. If suppose theta is not known, then what can be done is, say again, let us consider triangle OAB. Again a right hand triangle OAB. In that triangle, let us define tan theta. In OAB, tan theta is opposite. Opposite is AB, adjacent is OA. What is AB? D. D is nothing but thickness of the material introduced. Diameter of the wire, thickness of the blade or thickness of the paper paste. And OA is nothing but the length. I have taken as small l. Nothing but it is known as length of the air edge. L is the length, so that our tan theta becomes D by L. Theta small, so it is approximate to theta, so that theta equal to D by L. If you substitute theta in this expression as D by L, substitute theta as D by L, you get beta as lambda L by 2D. The fringe width beta, lambda L by 2D, lambda wavelength of the monochromatic light incident on the center, L length of the wedge, the distance from the point of contact to other end where the material is placed, D diameter of the wire or thickness of the material. So that from this diameter D is given by lambda L by 2 beta. If lambda is known, here L can be measured, beta can also be measured, so that D can be accurately calculated as lambda L by 2 beta. This is how thickness of the material introduced can be determined using this interference fringes. And this is about interference at an air edge. As I told, all the fringes are localized, fringes at the apex always dark, all the fringes are straight line and parallel, all are having equal thickness, all are equally spaced. And this is about interference at an air edge. With this I stop. We'll continue the next class with some other topic. Thank you.